That's fine. Don't worry about it. Just pretend it's not there. Well, we were about to jump to section 3, and we decided to stay right here just for a minute because you guys got some great questions, and I think they need to be answered because I've been hearing the same question from all of my classes. And the electronic design switch inputs and identification becomes difficult, not on Hall effects, which would be crank and cam sensors and distributor pickups. Those ones we can identify pretty easily. The ones where it gets a little bit sketchy would be the module-to-module communication ones. You know, like this PCM and ICM on Ford. You know, how is this being controlled? And I have on this one, this is a pull-up design. I'm reading second sentence. This is a pull-up design where the module supplies 0 to 12 volt square wave to the PCM based on the input from the crank sensor signal. And then the one before that, let's see, I have another one. This is a GM design on the ICM to PCM, the reference wire. I'm saying that the reference wire, this is a pull-up design, second sentence, where the module supplies a 0 to 5 volt square wave to the PCM based on the input from the crank signal. So I'm thinking of this Ford, actually, and I had a student ask me about this Ford, and he was doing a diagnosis on one, and this is one, if you guys want a video to watch to parallel this, watch the video that me and IDT did. One of the videos that me and Eric did, that he was here, and it was on a Ford truck. I think it was like a 95 or 96 Ford truck, and it didn't start. And we filmed live, and it ended up being a bad ignition. Wait, what was it? It wasn't an ignition module. It was a bad crank sensor. And on that circuit, what we were doing is we were controlling the. This is a little bit different of a setup. I'm showing this as an AC sine wave, where the one that Eric and I were working on was a 3-wire crank sensor, a Hall effect. This being the crank sensor here, and this wire would be going to the PCM. Anyway, watch that video and you'll get an idea of what I'm talking about and how we manipulated that circuit. I said in the video that it was a pull-down design. I think I called it a pull-down design. That it was the crank. See, this was at 10 volts, I think. I'm trying to get my bearings here on the difference between these two. This signal was reading 10 volts, and I knew that was my crank sensor signal. We were at the module when we did it. I took a test light, I believe, to ground, and I touched on and off of that, and I was able to make the coil fire. So now think about that for a second. The truck comes in, it's a no start, no spark, and it could be a crank sensor, it could be module. You'd all agree with that, even without going through schooling. You know, crank sensor, module, computer wiring. And what I did is I substituted that crank sensor signal, and I made the coil fire. And so if I made the coil fire down here, how is my ICM? How's the ICM?
Oh, good.
It's good. I can fire the coil. The ICM controls the coil, so if I can make that thing work, then I'm focusing toward the crank sensor, and that was the point in the video. And I guess the reason I'm saying variables with the electronic circuitry is that crank sensor really is not a pull-down design. It's a pull-up design on Fords. Why did it work with me connecting my test light to ground? Because the voltage before I started was high. It was at 10. And I knew that it was a 0 10 volt square wave, and I just simply needed to pull that to ground to make the module think that the signal was there. If I were to unplug this crank sensor signal, if this was truly a pull-down design, if I were to unplug the crank sensor signal, I would continue to have 10 volts on that ICM wire. And what you'll find on these Fords is you will not. So where's the 10 volt coming from? I would call this a pull-up design circuit. So how can I manipulate a pull-up design circuit? What you would typically do on a pull-up is you'd take your, say, test light. That's what I'm telling you to do here. Test light to battery positive. We can substitute this signal, make a signal for the computer, and the computer fires the injectors. Point being, test light to battery positive on a pull-up design. I just told you that this crank sensor is a pull-up design, yet I did what with my test light? I grounded it. Do you understand the variable or the confusion now and why I wanted to talk about this a little bit more? I want to give you some kind of a statement that says, we'll do this as a default if we're not sure. Okay? And that's what I just told you guys, and that is if, as a default, your signal voltage is high, and you know it should be a square wave pattern on that circuit, pull it low. If it's low all the time, pull it high. What tool you're going to use to do that? A test light. Can we use an LED test light? No. Most of the time, no. Some of the time, yes, depending on the circuit. I would prefer the incandescent test light here. It is a signal wire between modules. And I'm not suggesting you do this, say, on an engine computer to airbag module circuit. Does that make sense? There's limitations to where we're going to put a test light and just start toggling signals. We may not want to do that in some circumstances. It might be a problem. Yes.
Would it maybe not even be a bad idea to like make your own, like get I guess an inline fuse and like make your own jumper wire?
Fuse jumper wire. Absolutely, we want to use fuse jumper wires, but I have to warn you that a fuse jumper wire will not protect you here. Even if you put a 1 amp fuse in that jumper wire, that is way more amperage than these signal circuits ever see, if that makes sense.
Okay.
So a fuse isn't going to be our friend here. I like the bulb in the test light because if I would touch the wrong wire or, I kind of have a safety mechanism in there. Yes.
Is there like something that we can get from Snap-on to change our LED to an incandescent?
No, you want that LED test light. I'll show you there's times where we absolutely want to use the LED test light and not the incandescent. So what you need to do is you need to go buy another test light.
Well, I was thinking instead of buying another one, have one that you can like
No, you
swap
can't.
between it.
Nah. I mean, it would be just as easy to just get another light. An incandescent test light from Sears is like $20. You know,
You can get a cheap one from Harbor Freight.
you can get a cheap one for Harbor Freight, but you better make sure if you're getting that one from Harbor Freight that you're doing amperage measurements on that test light and make sure you're checking the amperage of your test light before you would ever use it on a car. And we'll go into that here, actually coming up in section 3 where we're going next. All right, so the difficult part in identification, if we look at this one too, it's tough. Because if I am trying to figure out the design here, what am I going to do? I would be unplugging the ICM, but when I unplug the ICM, I'm actually taking that circuit and I'm making that computer not be powered up anymore. Does that make sense? So we could misinterpret how that circuit's actually working potentially because we're making that module basically shut down completely. And I guess what I'm telling you is it is not clear sometimes on pull-up, pull-down circuitry when it comes to electronic switch inputs. What prompted that is the video we watched right before launch, at least momentarily, was that Lexus video where we have an igniter talking to an engine computer, and I think in that video I called that a pull-up design. Is it right? I went test light the battery positive. Let me pull that up real quick. Sorry for that minor distraction there. That's okay. We have a miserable pregnant girl amongst us, so that she's deserves a mulligan. That'll forever be recorded too.
See, even the hand on the screen is saying no.
Stop! Stop! Okay, I just pulled up the diagram. The video that I was just mentioning is this guy right here. It's the Lexus LS400 igniter bypass test. So you guys can watch the video at another time. And what brought this whole thing on was we were in the video. What I'm doing is I'm controlling these ignition coils. Maybe not. Wait, I have a pen out already. Hold on. We're gonna do this again. I'm controlling these coils here and here in that video by triggering igniter number 1 and igniter number 2. Okay? And what I did in the video, if you watch it, I looked at the IGT signal. The IGT signal on Toyota, Lexus is the signal that goes from the PCM or ECM and goes down to the igniter. So the top of this diagram, that's the wire that goes to the computer, and it says IGT. Stands for ignition timing or ignition trigger signal. Okay? The layout of this would be the RPM input, which would be cam crank, feed into this PCM. The PCM takes that information and is going to tell the igniter what to do in a digital format, digital square wave on that line. And so what I'm trying to do is, with this vehicle that doesn't spark and doesn't start, I believe that was the symptoms with the car, or maybe I just created that just to show circuit design. I don't remember if this was an actual no start case study. I apologize for that. I probably should have watched the video first. In the video though, I'm trying to be the computer, quote, be the computer. I say this in my text, be the computer and make that igniter fire the coil. And the reason I want to do that is if I can do that test, if I can take a test light here and create that signal and the coil sparks when I do it, I get spark coming out of this coil. I know my wiring is good to my igniter. I know my igniter is good. I know my wiring is good to my coil. I know my coil is good. And that'll make me focus toward the PCM and RPM cam crank signals. That's why I do this kind of stuff. How much time did I save?
A lot.
A lot. Now here's the complicated part. Engine computer is a module. Igniter is a module. We have module-to-module communication. What's my circuit design? Not totally sure. How I would go about doing this is I would disconnect the igniter, and with the key on, because I need the computer to be powered up. I need my 12 volts to come into the computer. With the key on, igniter unplugged, I would take a voltage reading on that IGT wire to ground. Make sense? And the result there will dictate what I'm going to do with that circuit. Or, I might even leave it plugged in. And again, this is one where you need to think about the circuit a little bit and how it works. That is a giant eraser. That's cool. Let's think about this logically for a second. If my cam and crank are coming in here, CKP is crank, CMP is cam, and I'm worried about my IGT circuit, in this module-to-module example, would the igniter be the guy that's pulling the signal to ground? Could it be a pull-down design? Logically, think about this logically for a second. As far as where the RPM, where the signals are coming in. What's doing the controlling? Is the igniter doing the controlling, or is the PCM doing the controlling? The PCM is. So just some logics involved here tell you that this cannot be, the igniter cannot be pulling that signal to ground. It can't be. The igniter's receiving a signal. So just going into it from that standpoint, see, I'm even confusing myself as far as, could that actually be a pull-down design circuit?
So where is it actually?
Wait, hold on, and this is good. I'm glad I struggled there. When we say pull up and pull down, we got a module here and a module here. Which module are you referring to when you call it that design? Which one's doing the watching, which one's doing the controlling, I think is an important part of this. And maybe it's pull down to one, but it's pull up to the other. And you understand why I'm struggling here. And do you understand why you guys would have questions with electronic circuitry and which way is it actually flowing? I guess I don't have an easy answer for you other than to say again this. If it's low, what do we need to do?
Bring it high.
Bring it high. I hate that tool.
I love that tool. So in
All
order
this
to
means is
actually-
I'm just gonna have to edit this one. That sucks, but well, maybe as long as that stops, I'll just leave that little interruption of the air hammer in there. If it's low, pull it high. If it's high, pull it low. What tool are we going to do it with? A test light. So I know for a fact that that computer is sending a signal to this igniter, and I don't know for a fact that. I was just thinking about this, right? What if the igniter sends 12 volts this way, and the computer pulls it to ground in here, making the square wave? Would that work? Could that work?
Yeah.
Yes. So that would we call that what? It'd be a pull down design, but then we're talking about the computer being the one that's pulling it down, and normally we're talking about the computer as the one that's watching. So you got one watching, one controlling, and I'm sorry, I apologize. I don't have an easy way to be 100% confident in these module to module circuits which way this thing is actually flowing.
Just call that one a pullover. It's pulling the signal over.
Could it also be that the computer is simply sending the signal in this direction and it's in a pull-up fashion, meaning the computer is generating the square wave independent of this igniter itself, and that's how the circuit works? And the answer is yes. So how would you make that determination with 100% certainty in this application? What could you do?
I'm not gonna lie to you, I think that's like trying to.
One of the things I can't do is disconnect the igniter and take a voltage measurement here and be 100% confident, because if I disconnect the igniter, aren't I taking the power and ground and everything away from that? And it could have been that igniter was sending 12 volts out, and now that I unplugged it, it's not there anymore, you know? So I called it in the video, that's what I did. I unplugged it, took a voltage measurement, found 0 volts, and so what did I call that circuit? I called it a pull-up design, and I plugged it back in, and then I took a test light here to battery positive, and I touched on and off that circuit. Now, I may not have done this step. Did I have to? No, because I followed my rule, which was what? Take a measurement, it was at 0 volts. What do we need to do to make the square wave on this circuit?
Bring it to 12 and there, 12.
Bring it out.
Sandwich has a
This probably isn't the best spot for your room.
And I even had insulation and everything put on the ceiling for this, but the problem is I have my own HVAC unit, and it's a microphone. It just pipes it right in. So it made no difference at all on sound in here.
That sounds like a little bit
No,
bad.
yeah.
Big cap yelling.
It sounds like a pirate.
Oh, it's kind of cool. I have Karen time to clean up in probably 100 videos. It's pretty cool. Yeah, I mean, she's got some pipes, man.
Yeah, she does. I
Yeah.
asked her if I could do it one time, and I really screamed. She's like, that wasn't loud enough. And she did it. I was like, wow.
Takes practice.
Yeah.
Okay, I apologize. That'll be chop.
Yeah.
I'm following this rule. If it's low, I'm going to pull it up using my test light. If it's high, I'm going to pull it down using my test light. Yes, Scott.
Okay, if the,
It is Scott, right?
yes,
Okay.
if the PCM is watching the igniter,
It's not.
so the igniter's watching the PCM?
It's not. The igniter's being controlled by the PCM.
Okay.
And that's a perspective I think we need to have too.
Okay, but if
On this circuit anyway.
the PCM is telling the igniter what to do, how is the PCM going to know what the igniter is doing if it's not getting a signal from it?
Okay, so you're asking me, that's a good question. On this IGT circuit right here, we are controlling, the computer is controlling the igniter on this leg right here, okay? It's telling the igniter what to do. It's really the base circuit control of the igniter circuit. Coil is here, right? igniter's here. Here's the redrawn of it. This would be coil positive. There's your coil. Your igniter is this guy right here. What's the igniter doing to the coil? It's grounding it, but it can't do it on its own. It needs to know when to do it, and that's where this base circuit of this transistor would come up to the PCM, and this is your IGT circuit. What's the IGT circuit do? It's controlling the base of that transistor. Now, it might not be directly. There might be a little processor in there that's doing it too, but that's essentially what that IGT circuit's doing. And your question was, how does the computer know if it's actually working? On a lot of our systems, it doesn't. It either works or it doesn't. If it doesn't work, the car doesn't start, and you have no trouble codes at all. I have a video on a Subaru. If you want to watch that, the title of that video is how to test an ignition coil with a test light, I think is how I named it. Just type in Subaru no start. You'll find that video. There were no trouble codes on that car, and it had a bad igniter. On this one, you'll get a code. Here's why. There's an IGF circuit right here. It stands for ignition confirmation. There's some other terms that they'll apply to that. So we have ignition timing, ignition confirmation. That what that's tied into, this IGF circuit on some of these, is they'll tie into coil negative, and this is my IGF circuit. Sorry, it goes to the PCM. IGF. And so as the computer is turning this guy on and off, and as the current's turning on and off on this circuit, we're generating an IGF signal that says we're good.
So is that why?
So that's what we would call a feedback circuit for trouble codes on this particular design. Not where we are here, but great question. So follow-up was what? Is that why what?
Is that why? So it makes it harder to diagnose a no start because there's no IGF circuit.
No, not at all. Not at all. I don't need a trouble code to give me guidance. The only thing an IGF circuit would maybe do for me is I have something I already know. The car doesn't start, number one. Number two would be if I see an IGF code, I would immediately go after ignition instead of maybe fuel or compression. So on a lot of these systems, guys, it takes 2 seconds to verify whether or not you have sparks. So you're really not saving a lot of time, and they're definitely not more difficult to troubleshoot. I apologize if I am making this more confusing about pull up and pull down between these modules, but this is something that I have often struggled with explaining myself, and there is no foolproof way, because if you're because what did I tell you guys to do with electronic designs, the Hall effects? Unplug them and check your voltage levels. The issue with the module to module is when you unplug it, you're killing a module completely. And so you may affect what that voltage level is, not because you unplug that signal wire, but because you unplug the entire module, and that can change the result. Jim?
Why hasn't it gotten to the point where manufacturers mark what system their vehicle is?
That is such a good question. I wish the engineers would wake up and give me this information. If they gave me this information on every circuit that's out there, I wouldn't need their flowchart. Sometimes I still have to rely on their flowchart because I'll look down the trouble tree and they might say, disconnect the igniter and make sure you have, that wouldn't be the case in this example, but disconnect the igniter, make sure you have 5 volts on that wire, and then if I know that's a communication wire, I'm looking at that and that tells me in that flowchart, that's a pull-down design circuit. That 5 volts is coming from the computer, and I know that that entire circuit from the computer down is good, and all I needed was that little piece of information. They don't give it to you. They don't give it to you.
We can make a book.
Well, you see at the end of section 2, that's why I had that list. If you look at the end of this chapter, I mean, I haven't updated this in a long time, but I just started writing down circuit designs on cars that I know about because it helps me later to reference this. If I'm working on now, granted, how many 1989 Hondas am I going to see? Not many, but I started doing that because I start seeing patterns. And one in particular that we just did a little bit ago was where's the GM mass airflow? I have to have a GM mass airflow right there. GM mass airflow, 3-wire. signal circuit's 5-volt pull down. PCM sends 5 volt to the MAF and the MAF pulls it to ground. I can use that on every freaking GM that's been made that uses a digital mass airflow, all the way to my, we just did a 2012 Cobalt that had a 5-volt pull down mass airflow. So even though some of this stuff seems outdated, is it really? Should we start adding to this list? That's why I put it here for you guys. Add to the list. I can put that note. Add to this list on your own. Why? Because the manufacturer doesn't give us this info, and it sucks that they don't give us this info. It really does. A lot. Because it would help me tremendously.
You should make Danner books like this, Mitchell or Chilton.
Do you know how many circuits there are, though? I mean, you're talking every single module to module circuit, or, crank sensor to...
Taking years
But how-
to get all those.
But here's the thing, too,
How
Jim.
many
If
people would buy it?
Yeah, I'm not. This is more about fixing the car and fixing it accurately than it is about making money. You know, I mean, it is ultimately about making money. If we can fix the car faster and more accurate, we're going to make more money. And the guy that's working next to us is a parts changer. He's going to, struggle along the way. I don't know.
You can start dating that and awesome kid.
Did you hear Anderson?
Come on, come to life.
It's a failing injector.
That's supposed to be a square. We're lagging again. It just doesn't like when I bounce back and forth and write in other programs and then come back in here and write and be a real suck.
It's a little temperamental.
Alright. I don't want to confuse you guys, but I'm not done with this. And I think it's really important. And this is not for some written test for you guys. This is really important when it comes to being under the hood of the car and knowing where to go and knowing how to make things work, right? Knowing how to make things happen. Igniter, PCM, communication line. The last one we did was the Ford ICM and the crank sensor. And I said the crank sensor was a 10-volt pull up. But in the video that me and Eric did, I took a test light to ground, and I grounded it, and I actually made the ICM fire the coil. Seems contradictory, but just the internals of the Hall effect. There's your magnet, and here's your Hall element with the transistor. If one of these windows that move past it are not in between with the key on, like stationary, the distributor's not turning, depending on where that window is, we'll either have 0 or 10. And if it's at 10, I'll just pull it down with my test light. And if it's at 0, I'll pull it up with my test light. And I really don't care. When do I care? If I'm doing this test and my test light lights, should the test light light on one of these signal circuits? And if the test light lights, then something's shorted. And if I want to make this circuit work, now I kind of need to know what that other component needs to recognize a signal. If that makes sense, probably doesn't. I need to just leave this thing alone. Trying to make it more clear. In the video, I called this a pull-up design, and I took a test light to battery positive, made it fire. I believe on that one, I left it plugged in, and I had questions, why'd you leave it plugged in? I thought you said to unplug it. Well, the reason I didn't unplug it is that igniter is going to shut down if I unplug it. And, really knowing circuit design is really not possible. The way you could do it is you'd have to take this one wire out, leave all of these ones still plugged in, and then take voltage measurements here and here, if that makes sense. That's the only true way that you could know that circuit design. Because now the igniter's alive, and the computer's alive, and you got the key on and nothing's going on, or you crank the engine over, you can figure out where this signal's coming from. That would be a way you could do it. If you were that hard pressed to figure it out, you can pull that wire out of that connector, plug everything back in, and do your research. Guys, this is research that I'm talking about here. So when I do this later, and I can troubleshoot a no start very, very quickly. That's the best I got. Any other questions on the module-to-module communication circuits? One more time, what's the rule we're going to follow? If it's low, make it high. If it's high, make it low. Use an incandescent light in most circumstances. I think it's also important to know the voltage levels on that circuit. It's important to know the voltage levels on that circuit. You may not want to use 12 volts, say on a 1 volt circuit. Although signal circuits are very forgiving because we're not carrying any current flow, they're just voltage sensing circuits. To refer you to one in particular, I'll do this on oxygen sensors too. And on an O2 sensor, we produce 0 to 1 volt, and I'm taking a 12 volt test light and I'm triggering the computer to recognize a rich signal on an O2 sensor. We're going to be getting to that. Ford Taurus, you want to see that video? Type in Ford Taurus O2 sensor and you can watch me do that test. On a 1 volt circuit, I'm taking a 12 volt test light and I'm driving that voltage high. Did I hurt the circuit? No. What has given me confidence to do that over the years? I get these cars that come in and you got this melted harness. Harness is melted, laying on the exhaust. And the 12 volt feed is feeding into a 1 volt O2 harness. And it's been like that for a couple days. They've been driving the car. Fix the wiring problem and everything comes back to life and works normally. So what have I been seeing over the years with these sensing circuits? Too much voltage in that sensing circuit, just take that voltage away and everything works fine again. We don't hurt anything. It's not the case in section 3 where we're going next with outputs. We can hurt things. But this signal circuits were a little bit safer. The only thing I've ever seen cook a signal circuit on a car was a melted harness on a Chrysler, and it had low voltage wires to a sensor that were melted into the fuel injector control wires. And when fuel injectors turn off, the magnetic field collapses and you'll get 120 volt spikes on that fuel injector circuit. Did those 120 volt spikes hurt my sensing circuits in this computer? They did. So is there a level of voltage where we could hurt a sensing circuit? I saw it. It cooked the sensing circuits on this particular Chrysler. The map sensor, when it was done too, it needed a computer. It cooked the computer. It needed the harness. It also needed the map sensor and fuel tank pressure sensor. It didn't hurt the potentiometer, the TPS, or the thermistor, the coolant sensors, because they don't have electronic circuitry within them. It cooked the map. It cooked the tank. Any pressure sensor it cooked on that car. 120 volt spikes. Be careful with bypass testing. But bypass testing can be your friend. Okay? All right, I'm going to let you guys take a break. When you come back, don't move your chairs yet. When you come back from break, we're going to start section 3. Okay?
Okay.